Well, welcome to the seminar. Our speaker today is Dr. Bob Bindschadler. He's going to give us a talk that I saw probably something very similar last summer at a conference in Montreal, and I thought it was such a really wonderful talk that made the effort to have him come here and give it to all of you. So Bob is sort of officially retired and unemployed at the moment. He was the chief scientist at NASA's Hydrospheric and Biospheric Sciences Laboratory, a senior fellow at the Goddard Space Flight Center, and he's a fellow of the American Geophysical Union and a past president of the International Glaciological Society. He got his undergraduate degrees in physics and in astronomy from the University of Michigan, and then his PhD from the University of Washington. He's very well known in the ice community. He's testified before Congress and briefed as vice president. He's published over 140 papers in the work related to this talk here. So I'd like you to welcome Bob Bindschadler, and he's going to talk to us about waking giants, ice sheets in a warming world. Thank you, Bob.
Thank you very much, Ian. It's a pleasure to be here. There's snow falling in my hometown, and not here, but I'm going to be treated to your hospitality for an extra day, Southwest Airlines tells me. So I'll enjoy that. But it is a pleasure to be here. I like talking on this subject because it's such an interesting subject. In preparing the talk, I did try to learn a little bit about the Charles C. Jones seminar series. I still don't know who Charles C. Jones is, but I read a little bit about the seminar series, and actually looked at some of the videos of some of the previous presentations. And you've been treated to some very high-quality presentations, and I hope I can match that today. I also read that a number of you are not here of your own free will, that attendance is required. So I thank the other of you for coming. And for those of you that have to be here, I do have another message, because you are the PhD students. And I want to introduce into your heads maybe a trace of doubt that maybe you're in the wrong field. And you want to be a glaciologist, because there's no better time to be a glaciologist. I timed it totally wrong. 30 years ago I started to do the glaciology, and only in the last 5 years has it really gotten interesting. And so that's actually a lot of the message I want to give to you today. That the observations we've been making of ice sheets, a lot from the ground, but just a lot of them from satellites, have just absolutely astonished us. They are not the ice sheets that I was studying in graduate school. They are doing things that we didn't think they could do, changing at magnitudes and rates that we just never thought we would ever witness. And so I want to show you that today, and some of our thoughts about not only what they're doing, but why it matters to you. Why it's important. Why it's important for you to know that these things are happening. We are working very hard on trying to figure out why they're going on, so I'm going to talk about the causes. And then it wouldn't be fair to you to talk about all that stuff without at least mentioning what we think is going to happen. So I will touch on the issue of predictions towards the end. I'll try to cover all of that and then still leave some time for some questions. One of the most amazing things we've seen ice sheets do, and these are ice shelves. This is the floating fringe of a grounded ice sheet as it flows into the ocean. It's still hundreds of meters thick, but it's stiff enough it can rest on the ocean, and that's what we call an ice shelf. They take thousands of years to form. But we have seen in case after case after case in the Antarctic Peninsula that they have disintegrated. At the end of a warm summer, they will just break up and disappear. And actually, the sequence of images here on the right kind of illustrates just a series of images taken over the course of a few weeks that, for all the world, it just looks like that ice shelf just exploded out into the ocean. This is not something that happens every week. because they take so long to form. That's the Larsen B ice shelf disintegrating. It did it in 6 weeks, and it took at least 10,000 years for that ice sheet to form. So it's not going to do it again for at least another 10,000 years, if ever. So that's one amazing thing. That really caught us off guard. And as I said, it's happened a number of times. So this is just a larger scale view of the spine of the Antarctic Peninsula in 1986 on the left. And then what that peninsula area looks like now, recently, a few years ago in 2006. So you can see that these ice shelves are major features. And we're losing them. We're losing them one after another on both sides of the peninsula. And that, as I said, that gives us cause for concern. I'll speak a little bit more about that in a moment. Another big surprise is when we monitor the speed of ice discharging ice from the interior of the Greenland ice sheet. It gets funneled into these large outlet glaciers that go faster and faster as they move towards the ocean. And so this can be done with interferometric techniques with synthetic aperture radar data. The technique isn't so important as what we've seen, the changes that we've seen here in the case of monitoring some of these outlet glaciers. And that's illustrated by the plots on the left. And these are plots along the center line of a particular outlet glacier as it goes from fairly slow speed on the left over here in the case of Kangerlussuaq. It goes fairly slow in the interior and then goes faster and faster as it flows out towards the coast. And the black curve is the speed of these 3 outlet glaciers from the interior out to their terminus in the era of, can't really read that screen there. My eyes are too bad to read that one. So in the late last century. And then we checked it again about 5 years later, and most of them were going about the same speed. And then just over the course of the next 5 years, so now we're talking about the interval there in 2005, they were going much faster. Kangerlussuaq definitely much faster, about 200% faster. Helheim about 60% faster. Jakobshavn actually got an early start, and it was already rumbling along at an accelerating rate right there around the turn of the century. So these are not small accelerations. This is not little ice. These are huge ice streams moving cubic kilometers of ice per year. And they were starting to drain the Greenland ice sheet faster. That caught our surprise. At the same time, this is some more details of Jakobshavn, sort of an aerial view of what the fjord looks like when that glacier was retreating. It's just choked with these big icebergs. There's some stunning videos. I didn't bring any of them with me. Stunning videos of the calving front of the Jakobshavn glacier. Just these huge building-sized icebergs calving off and rotating and popping up from underneath. Very dynamic environment. Calving much faster than the flow of ice can replace that ice, so the terminus of the glacier retreats up the fjord. This process has been going on through the last century and a half, and you see there on the lines on that map where that terminus position was starting in 1851 up to nearly the present time. And it retreated 10 kilometers in about 50 years from 1851 to the end of that century. And over the course of the 20th century, the first half of the 20th century, it continued to retreat at about that same pace, 10 kilometers in 50 years. It had a still stand for 40 years. And then suddenly in 2000, actually late 1999, it started to retreat much faster. And the next 10-kilometer retreat took only 5 years. Not 50 years, but 5 years. An order of magnitude faster retreat of this particular glacier. So it really woke up. And this drains at least 10% of the Greenland ice sheet. This one glacier really matters. It is the fastest glacier in the world. It would, in the course of this lecture, move from that wall to that wall. It's really rumbling along. It's moving so fast that when you're standing next to it, you can see it move. The only glacier, I think, in the world that you can really make that statement. But you can see it move. It's that fast. One thing glaciologists like to do, just sort of a index that gives us the state of health of an ice sheet. It's called mass balance. And all that means is it growing or shrinking? Is it receiving more mass through snowfall than it's losing through either melting or flow of the ice back into the ocean? If the mass balance is positive, it means it's growing. If it's negative, it means it's shrinking. And if it's shrinking, that means it's putting ice back into the ocean and sea level is going up. The purpose of this slide is just to say that a lot of people are trying to quantify the mass balance of both the Greenland ice sheet and the Antarctic ice sheet. I should say, for those of you who aren't that familiar with ice sheets, Antarctica contains 90% of all the ice on the planet. And Greenland contains 9% of all the ice on the planet. Antarctica is 10 times larger than Greenland. And that only leaves 1% left, just sprinkled around the small glaciers around the world and ice caps and things. It really is the two big gorillas in the room are Antarctic ice sheet and the Greenland ice sheet. And regardless of how we measure mass balance, whether on the left here on Greenland, the first map of Greenland is mass balance as measured by the change in the surface elevation. We've got satellites that measure surface elevation very precisely. Over time, we see that elevation change, and if the ice sheet is growing, we see the elevation go up, and where it's shrinking, it's going down. And that gives us a very good map of locally where it's growing and where it's shrinking. And overall, it's shrinking, especially at the margins. And again, I'll pick up on that point in a moment. There's a completely different satellite, GRACE satellite. It measures gravity. And I won't go into details of how it does that, but it measures it precisely, but it has sort of blurry vision. It can only measure gravity over a fairly big area. But Greenland's a really, really big area, so it does a pretty good job of measuring how the mass of the Greenland ice sheet is changing over time. And it can look at broad regions, and it says basically the same thing, that Greenland is losing mass. Completely independent sort of verification of that, what the elevation difference told us. Or you could measure how rapidly ice was flowing out and how rapidly snowfall was falling onto the ice sheet. And again, do the math and come out with another mass balance calculation that tells you whether the ice sheet's growing or shrinking and where it's gaining or losing mass, catchment area by catchment area. And that's the middle, the final plot for Greenland on the right there. And you can do the same for Antarctica using elevation change or this velocity and accumulation budgeting approach. And regardless of what technique you use, you find out that the ice sheets are losing mass. But scientists love to disagree with each other, so they'll disagree about the details. And actually the press made a big deal about, well, the science community doesn't seem to know how fast the ice sheets are shrinking, or if they're shrinking at all and where they're shrinking. But actually there wasn't that much disagreement at all. And I think the best illustration of that is this one for Greenland. And all these colored boxes on here represent some of the published papers that were attempting to quantify the mass balance. And so the apparent disagreement really is apparent, and it's not actual, because the mass balance is changing over time. So if you take all these published estimates, as represented by these color boxes, and you place them on a time axis down here, according to what time period the data were collected, so whether they're talking about the mass balance sort of in the early 2000s or in the early 1990s, you place them that way, and the height of the box just represents the uncertainty. It really paints a very clear but disturbing picture. Or just in case you don't get it, that's what the arrow is for. It says that Antarctica a few decades ago was pretty much in mass balance. It wasn't gaining or losing mass. But recently, it's been losing mass faster and faster and faster. That's a disturbing picture. That means sea level is doing just the opposite. Sea level is doing this. And in fact, we see that in the sea level record. So we all really were agreeing. None of us was exactly right, but all of us were right sort of in the aggregate. Antarctica, 10 times the size. It's harder to collect all these data sets. A lot of it hides in the polar, right around the pole where some of the satellite data don't exist. But But if you plot the data, the published estimates the same way, you kind of get the same picture. It really does hint at the same kind of accelerating loss of retreat, accelerating loss of ice. So we can say, definitely, from direct observations that ice sheets are changing, and they're changing fast. And the accelerating rates of change, I guess I really should say increased rates of change as an acceleration, aren't the exception anymore. That's the rule. That's the ice sheet that we see today. Very different than the ice sheet just a few decades ago. Why should you care? Because it matters globally. That ice is going into the ocean and sea level is going up. Half of the world lives very close to the coast. Half the world. That's 3 billion people. And just to make that point even stronger, all the plots on this chart, the red spots, are places on the planet where they are within 1 meter of sea level. They're within that far of sea level. So if sea level goes up 1 meter, all those red spots will be new ocean. There won't be land anymore. And a lot of people live in those areas. To put some actual numbers on that, that's what I use this chart for. Sort of break down continent by continent. Asia is the big loser. And you can think about, well, the pictures are of the Maldives. I mean, they have built right up to the shore now. And they are fighting sea level on, it's a daily issue for them. But it's not only in the Maldives. I mean, that island nation, I mean, the prime minister there, sort of as a PR stunt, but it really made the point. He held the first cabinet meeting underwater. All his cabinet ministers put on scuba gear and they went underwater, because their nation is going to be underwater within the next couple centuries. And all the people that live there are going to have to live somewhere else. And that is pervasive throughout Asia. You can see in that middle chart that over 100 million people that live in Asia right now live within 1 meter of sea level. You can think about the Irrawaddy Delta. You can think about Bangladesh. I mean, millions of people are going to have to move by the time sea level goes up 1 meter. And I'll say a little bit later here why we think that's going to happen this century. Before the end of this century, sea level will be 1 meter higher than it is today. And if you want to put it in economic terms, that's what the final chart is, that Europe has an awful lot of their very valuable land where the industries are located within that 1 meter of sea level. So the loss of gross domestic product approaches $1 trillion, which used to be a big number. Not a big number anymore. I know, I live just outside DC. But it still is a big number for most people. I don't think most people can write a check with that many zeros on it. And as I said, sea level has been rising. There have been lots of records of sea level, and you can see that during 2 centuries ago, sea level was going up about 1.5 millimeters. Over the past century, it's been about 2 millimeters a year, and the most accurate measurements now are pushing that 1.3 millimeters a year to 3.8 is the highest number I've heard most recently. It is accelerating. The observations are direct and irrefutable and unequivocal. It's happening. We're seeing the signature of the loss of ice. The IPCC, which I'm sure most of you know about, the Intergovernmental Panel on Climate Change, which received part of a Nobel Prize for this latest report of theirs, the 4th assessment report. The IPCC does a great job of trying to synthesize our state of knowledge of climate and how it may be changing. In their last report, this is their breakdown of what was responsible, the different components and their relative contributions to the increasing rate of sea level. And actually, thermal expansion of the ocean has been the major component over most of that multi-century record that I showed you. It was more than half of the sea level rise was attributable to just warming up of the oceans. And the glaciers and ice caps, even though they're only 1% of the land ice on the planet, they were responsible for about 1/4 of it. And the ice sheets actually were fairly small components, but their relative contribution is increasing rapidly as as you know, that arrow is going down and it's losing ice faster and faster and faster. So this is the old view, and that ocean thermal expansion, that rate can't really increase very much, but the ice sheets are showing that they can come on strong here in the last few years. So this pie chart distribution is substantially changing. But that was the view from the IPCC's last report. This also is a table that comes directly from that report, where and I've spoken with Susan Solomon, who led Working Group 1, and she was required to put this chart in there and fill it in with numbers. These numbers on the right are the estimates from different scenarios, you know, how the world might evolve, how energy usage might evolve over this century from now until to the year 2100. So they had paint different scenarios where there's business as usual, and there's sort of more energy conservation scenario, and even a more a less conservative energy use scenario. So they get a range of estimates. And on the right, they run these fancy models and they produce estimates of how high sea level might increase based on the energy use scenario and how climate evolves with that increase in production of carbon dioxide gases and other greenhouse gases. The highest number you can find in that table is the one I underlined, is 58 centimeters. So the worst scenario in terms of climate change that they were considering. And so I just posed the question here, is that actually the worst case? And it's not, and although the press picked up on this, that number was less than the previous report, and they said, the headline is the scientists are less concerned about sea level rise. Well, they only looked at the numbers, and they didn't read the words, which I'm sure you're never guilty of. So let's read the words here. Model-based range excluding future rapid dynamical changes in ice flow. That's like you making your budget without taking your mortgage into account. And there are more words. And, you know, shame on the journalists that didn't read the words. I mean, they live by the words. These are other words that you can find on the very same page that say but flow rates could increase or decrease in the future, and larger values cannot be excluded. So that's clearly not a maximum. It was just based on the models and the requirement that they come up with this table and fill in numbers. Those were the best numbers. These words say, don't believe the numbers. The numbers exclude the most important component. So, but that was a really good report. As much as I may sound like I'm critical of the report, they did the best they could at the time. Let me illustrate this point another way. I'm going to sort of harp on this concept of mass balance again. It really is pretty simple. You know, it is just adding snowfall, the accumulation term. And for Greenland, last century, when it was more stable, the accumulation amounted to a term, units probably mean nothing to you, gigatons per year. But a certain amount of snow falls on the Greenland ice sheet. And the other two processes that remove mass from the Greenland ice sheet are melting around the edges in the summertime and ice flows, or all the time. And they were approximately in balance. Melting and ice flow accounted for about equal amounts of ice loss, and the sum of those two matched accumulation. That was last century's ice sheet. This is this century's ice sheet. And the reason I draw it this way is that it says that the accumulation will increase. As the climate warms, the atmosphere can carry more moisture, snowfall will increase. That actually has been measured, occurring in Greenland primarily. And the climate models, for all their warts and dents, are pretty good at estimating how much it's going to increase. They handle water vapor and its movement in the climate system pretty well. And they say it's going to increase by about 10%. Okay. Melting. Well, in a warmer climate with warmer summers, melting is going to increase too. And again, the climate models are really pretty good at getting a credible handle on that number. And they say melting is going to increase by about 50%. So already you're starting to lose ice. What the climate models just absolutely suck at, sorry, but they do, is this last one, ice flow. They don't get ice flow right at all. Even the specialized models that are designed to be able to simulate ice flow can't reproduce the dramatic changes that we've been seeing just in the last few years. We have no good models. But the measurements tell us that ice flow can accelerate a lot really fast. So we don't know how much this can increase. We've seen it in individual cases increase that 60% that in 5 years, that 210% in 5 years. We've observed that. That's not a model. Those are observations. So it could be a little bit better because there's slop in these numbers, or it could be a lot worse. It depends on how ice flow changes. So now I want to get into the part of the talk where I talk about what we think may be the cause. And I like to pause here after posing this question because I have a one-word answer to this. I won't put you on the spot to see if you know what the answer may be, but it's a one-word answer. It's water. Water is the agent of change that's just killing the ice sheets. And I'm going to explain how that works. But if you can remember 4 words from this lecture, these are the 4 words I want you to remember. Ice sheets hate water. It just kills them. Which seems so ironic because ice sheets are made of water. But man, water is hot if you're an ice sheet. Hot, not in a good way. 3 different ways. I've never seen a sexually aroused ice sheet. So. One way it tears ice sheets apart. Remember those ice shelves that disintegrate? We think what's going on there is that ice shelf is made up of some pretty rapidly moving glacier ice that flowed into it, and it's full of cracks. We know that. We've seen those cracks. And in a warm summer, a lot of that snow melts on the surface, and you get a lot of water. Actually, in this sequence, right there, all those blue spots are lakes on the surface of the ice shelf. And so they fill up these cracks. But as long as they don't fill up the crack all the way to the top, that's a stable configuration, not a problem. And so the cracks within the surface of the ice shelf can absorb a lot of water. But if you have even more than a little bit of water, you have enough water to fill up that crack, all you have to do, you guys are engineers, the forces at the tip of that crack are a balance between the ice squeezing the tip shut and the weight of the water trying to open the tip. And because water is heavier than ice, if that's full of water, the water wins. The crack opens up, it deepens, the water level goes down. But if you have more water, the reservoir there on the surface, and can keep topping up that crevasse, keep it full of water, that water will work its way all the way through and work that crack all the way through the ice. There's absolutely no reason it would ever stop if you can keep that crack full of water. So just having enough water is sufficient with these cracks, and they're there, to break up the ice shelf. It just chops it up like a sushi chef's knife. And so now you have all these tall, thin blocks of ice, and they're unstable, sitting in the ocean that way. And they all just want to fall over like dominoes, sitting up on their tall end. And that's exactly what our interpretation of that imagery, that thing. That color is the inside of the ice shelf. That's glacial ice, that beautiful powder blue color. So we think what we're really looking at are a whole bunch of small icebergs, small enough we can't resolve most of the individual pieces, that have just fallen over. And so it looks like, they've just kind of pushed their neighbor farther out into the ocean. So it looks like the ice shelf has exploded, but it was water that chopped up that ice shelf. Now, I've already emphasized that the principal concern is one of sea level. This is floating ice. You can do with it whatever you like. It's not going to change sea level. So the issue here is really what happens to the ice that's not floating, the ice that's still grounded up in the mountains there, the Antarctic Peninsula. Does it notice that ice shelf is suddenly gone in a matter of a few weeks? Our community debated that viciously for 20 years. The ice shelf matters. The ice shelf doesn't matter. It only cares about local stresses up at the base of the ice and on the sides. Well, Mother Nature came along and said, I'm going to get rid of this ice shelf. Boom, you're gone. You're out of here. What do the glaciers do? They sped up. They noticed big time. They sped up a factor of 4 and a factor of 5 in just 2 years. So without that ice shelf, that really was the valve, that really was the cork in the bottle. And when that ice shelf went away, the glaciers accelerated. So now you've got a sea level signature here, because that was grounded ice that was happily sitting up out of the ocean. Get rid of the ice shelf, flows into the ocean, and sea level goes up. And these are just small ice shelves. There are some really big ice shelves in Antarctica, and those are the ones that we're concerned about, because they're holding back huge volumes of ice, volumes that can raise sea level not just a meter, but meters. So ice shelves matter. Ice shelves do buttress the grounded ice. Okay, and water is the culprit. That's how you tear an ice shelf apart, disintegrate it quickly. What else can water do? This is sort of the iconic image. To my community, I don't even have to say the next 5 minutes. All I do is show this image, and they know what the story is. This is the melting, intense melting at the margin of the Greenland ice sheet, where that water flows into lakes, and the lakes drain through rivers, and the rivers get really scary big, and then they go into holes, and they make huge moulins that you can drive dump trucks and other, throw small buildings into. I mean, it's really big scale, scary hydrology. Well, where does that water go? And does the ice sheet care that it's lost that water? Nobody ever bothered to measure it for a long, long time. And then a colleague of mine went and put some GPS up on the surface of the ice sheet and noticed that when all this water was formed and flowing into the ice sheet, that the ice sheet went faster. It wasn't that huge a surprise because we knew mountain glaciers acted that way. But people have tried to follow this water all the way down. There's a good job for a grad student. They've only gotten about 100 meters. The ice right there is about 1,000 meters thick. You get wet and cold, but they didn't get down to the bottom, and the water just kept going. This is what we think happens. And again, there's no reason that water is going to go anywhere other than continue to go down until it can't go down anymore when it hits the impermeable bed beneath the ice sheet. And then it's going to flow along that interface, and it's going to lubricate the ice sheet. We haven't seen it, but we've seen the evidence of it in the GPS record that tells us that the ice flow increases. That's just the record from the paper that really nailed this. This is how much melt is going on, the red curve, and then the red curve up there is the speed of the ice. And it says that every time melt is occurring, the ice is going faster. So we do think water, again, has this additional effect that it can lubricate the base of the ice sheet, and if you add more water and it can get to the bed, it will speed up the flow. The numbers are still kind of all over the map. If you have really fast moving ice, there probably is some water. You add a little bit more water, it doesn't notice too much, it just increases a little bit. But if the ice was really slow and the bed was pretty dry and all of a sudden it goes to a lubricated state, it actually can almost double its speed. So there's some big numbers in here, and again, it's lubricating a large part of the ice sheet, so a lot of ice is getting moved faster into the ocean. This is important, and people are working very hard to figure out sort of the details of just how important. And it's going to become more important, as I'm trying to illustrate here. If you want to see these lakes, you can go to Google Earth and zoom in on Greenland. You can see those blue spots. Those are big, shallow lakes, and that's where the water comes from to form these rivers. And it's generated by the melt that occurs around the margin, and the areal extent of melting around the Greenland ice sheet is increasing over time. That's sort of what I'm trying to get across here. And you would expect it to increase. And as I put on an earlier chart, the climate models are pretty good at saying there's going to be more and more melting over a larger and larger portion of the perimeter of the Greenland ice sheet. And the statement on here is from the data directly that the more melt you have, the faster the ice goes. So I'm going to stay focused on the margin of the ice sheets because that's where these changes are taking place. In this particular slide, the colors represent the change in elevation. So this is from the satellite altimeter data, and it indicates where the thinning is taking place. And that's primarily the greens and blues. And the blue areas sometimes are so concentrated spatially that they can't even see them underneath these little sort of attention-getting explosions. But that's where the changes are taking place. In Greenland, those three explosions, those were those three rapidly accelerating outlet glaciers. But we see some of the same signatures in Antarctica. So it's not limited to Greenland or Antarctica. Both ice sheets are showing this behavior. But another curious thing about these locations, this is where not just any outlet glaciers are discharging the ice, it's where the deepest outlet glaciers are discharging the ice. And we think that's a really important characteristic that sort of gives us an additional clue to figuring out what's going on. And I want to introduce this bit of data because it's important. This is focused on these ice shelves again, the floating fringes fed by the outlet glaciers. And what the chart on the left says is that how fast you melt these ice shelves on the underside depends on how warm the water is. Okay, it makes sense. The warmer the water, the faster the melt rate. And again, back in my grad school days, we were nervous about any melt rate more than 10 meters per year. We just didn't think that existed. Well, we're now directly measuring melt rates that are 200 meters per year. And they've always been there, we just didn't know that they were occurring. So but the other important point about this chart is that you don't have to increase the water temperature very much to get a significantly large increase in the melt rate. And the melt rate matters because, okay, you don't disintegrate the ice shelf, but you melt it more and more rapidly, you're thinning it. It's sort of the disintegration case in slow motion, if you will. Because as you thin the ice shelf, it has the same effect as disintegrating it, just not as large a magnitude of an effect. So, but it is sensitive to water temperature. Just a slight change in water temperature can really change the melt rate a lot. But I said it was the deeper outlet glaciers that were sort of exhibiting the greatest change. And that's because of this other effect, that the melting point of ice decreases as you increase the pressure. And if you have really deep ice, it's under high pressure, and its melting point is actually quite a bit lower. So water feels hotter to it. Water at 0 degrees is going to feel hotter to ice that has a -1 degree melting temperature because it's going to see a 1 degree temperature difference as if it were at sea level and it just had 0 degrees. So, well, that's almost ice. I don't care about that water. That deep ice does care about that water because it's at -1, not 0. So the deeper ice is, so we think it is this impact of the water temperature affecting the melt rates that is cause for us observing that it's the deepest outlet glaciers that are reacting most vigorously. Another really, really nice study that was done that emphasizes this point, that it's a water temperature that matters, is this paper. I highly recommend you read it. This is the figure from the paper. And it's focusing on Jakobshavn Glacier, just sort of year after year after year. So Jakobshavn Glacier is here, and it started to retreat sort of rapidly actually it was 1998 when it started to retreat. And the colors here are the temperature inferred from fishery records for fishing villages along the southwest coast of Greenland. What they do, they go out and they catch fish. The type of fish they catch depends on the temperature of the water. And they were able to keep records of how much of what type of fish they were catching. And it became clear from that record that fisheries farther south were catching a more warm water loving fish in greater quantities in the earlier years. And as time progressed, that same characteristic was experienced by fishermen farther and farther up the coast. And so that's indicated by the colors here that give some indication of what the temperature of the subsurface water is. These aren't surface temperatures. That's why satellites never saw this. But it was really clear from taking those data and analyzing it that way, just for temperature, that there was a warm water subsurface, warm water tongue working its way up the coast of Greenland. And by the time it got into Jakobshavn Fjord, where the Jakobshavn Glacier is, boom, that's when that glacier started to retreat. So it was the delivery, the arrival of that warm water that almost certainly initiated that sudden retreat. So this is sort of our cartoon of what we think is happening in the Antarctic. This is a project that I'm directly involved in, where, okay, we're on an ice shelf, and it's fed by a fast-moving glacier, and that glacier sort of eroded out a deep trough in the bed. And I've got a number of slides at the end, but I don't think I have time to go through the details. So let me try to be quick about the story here. That tropical ocean, 2 layers. Warm on the surface, cold beneath. Polar ocean, 3 layers. Cold on the surface, cold on the bottom, and warm in the middle. And in the case of the Antarctic circumpolar current, the warm water sits as a plug called circumpolar deep water, and it sort of lurks just underneath, just below the continental shelf break. And there are processes going on in the atmosphere affecting the ocean circulation that it's causing the circumpolar deep water to upwell onto the continental shelf. But the first place it arrives, can get onto the continental shelf, is in this trough. So if you're upwelling circumpolar deep water, the first place it gets onto that continental shelf is right in this trough. It's salty water. It's denser than the cold water in here. And it just sits in that trough. The seabed is tilted towards the ice sheet because of the weight of the ice sheet. And just gravity makes it move down towards the ice sheet. This trough steers it right towards the glacier. And again, this pressure effect makes that feel really hot, like really hot water to that glacier coming to float here. It melts ice like crazy, thins the ice shelf, and that glacier accelerates. That's what we think is going on, and we're hot to go to the field to find out what the actual numbers are. But I think I already told you, models are no good. The field work is just kind of getting started, trying to chase down some of these details. But, you know, as Ian said in the introduction, I get called before Congress and they say, you know, what's sea level going to do? We want to know. And how are we going to answer that? Well, actually, let me give you sort of the various approaches that our community is following are these. You know, we can look at history. That tells us a lot. I'll give an example in a moment. We can do extrapolation. Say, well, these glaciers are doing that. What if those glaciers did what these glaciers are doing? What would it look like? We can use proxies. I'll give an example of that. And then we can use analogs. So if I can cover all of that in the next 15 minutes, that'll be good. Okay, let's look at history. What I've put together here are 2 records, one of temperature and one of sea level. And you're supposed to be convinced that every time the world has gotten warmer, there's less ice and sea level is higher. We've got 1 million years of paleoclimate history that tell us this. So there's absolutely no doubt in our minds that because the world's getting warmer, there's going to be less ice. So sea level is going to go up. That part we know. It also says that ice sheets shrink a whole lot faster than they can grow. And again, this just harkens back to the fact that they can shrink by increasing the flow of ice. And that's easy to do over short time scales by large amounts. And we're witnessing that. They can only grow by increasing snowfall, and that never increases that much, that rapidly. So it does take much longer to grow an ice sheet than it does to shrink it. And there's variation. There's going to be a lot of journalists get excited, you know, over little blips in the curve. But I think that's all going to be noise in the system. So when I get called to testify and I'm asked these hard questions, I love to give them the easy part of the answer. It says, yeah, sea level's going to go up. Absolutely no doubt about it. But the hard part is how much and how fast. And that's what we're working on through these various lines of investigation. History was one, so that sort of gives us the big picture and that easy part of the answer. This is the best paper I would submit to you as an example of this extrapolation approach. And what it did was it looked at the most dramatic changes in glaciers that we've observed. And it said, okay, if those glaciers can do that, what if other glaciers did the same? We're not going to ask any glacier to do anything we haven't seen at least one glacier do, but let's just make more glaciers do that. How fast can we raise sea level? How fast can we discharge ice from the ice sheet? And it turned out that by 2100, playing games with the numbers and actually pushing a few glaciers to do even some more dramatic things that we haven't seen them do, you could get it up to 2 meters. But you really had to start imposing this very dramatic behavior and even beyond what's been observed to get to 2 meters. That really seems like a pretty hard upper bound. But if you don't ask any glaciers to do anything that we haven't seen glaciers do already, it's not hard to get to 0.8 meters. That's pretty easy. So we think this is definitely in the realm of possibility. This is kind of near the upper bound with this kind of approach, which is a legitimate approach when you don't have anything else to work with. So 1 meter sort of fits in there pretty nicely, comfortably. This is my example of what I call the proxy method. And this is a really nice study that came out just after the IPCC report done by Stefan Rahmstorf. And he said, okay, let me look at the data of how fast sea level has gone up in the past and how warm was the climate then. Let me just pair those numbers together. A little bit warmer, sea level goes up a little higher. A little bit cooler, sea level doesn't go up quite as fast. And he put those together on these points on the chart and just empirically came up with a relationship of if the climate is warmer than this mean than this 1951 to 1989 mean, it's a little bit warmer, sea level's going up faster because it's doing this right now. And actually it's going a little higher. And if it's cooler, sea level doesn't rise as rapidly. Okay, so he's got this relationship. Then he goes to the IPCC models that are pretty good at predicting temperature and says, let me just apply that relationship decade by decade to the IPCC predictions of temperature through this century. And how much has sea level risen by the time I get to 2100? And again, through the range of scenarios, he gets a range of sea level rise that's 0.5 meter to about 1.5 meters. So again, 1 meter is right in the middle of that. So it's a pretty comfortable number when you take these approaches to sea level change in the future. One more analog, and that is, we've seen a certain class of glaciers called tidewater glaciers do some dramatic things in the past. A lot of these are in Patagonia and maritime southeast Alaska. Tidewater glaciers are glaciers that come out of the mountains and they go into a fjord and they displace the water, and then they have a floating terminus. And they have this mode of retreat called drastic retreat. Fancy term. So, and what we think is happening, well, what we're sure is happening, is that as the glacier, in the good times, positive mass balance, glacier wants to grow, it advances. It can't advance very quickly, but it does advance, and it pushes the moraine out with it, and that moraine provides actually a very shallow place for the terminus of the glacier to sit. It doesn't want to sit in deep water because the calving rate is proportional to a high power of the water depth of the terminus. So it can't accelerate, can't advance quickly because it can only accelerate as fast as it can push this moraine out, and that's an erosional process, and that's pretty slow. But if it retreats, so if it tries to jump out here, then it gets knocked back. If it retreats off of that, again, it finds itself in deep water, and it can retreat, and it will retreat, and it does retreat. And it gets into deeper water, retreats faster, and it gets into deeper water and retreats faster. And it won't stop retreating until it's gone from there all the way either to shallow water, in some cases all the way up out of the water. So it does that transition pretty fast, at 1 kilometer a year. It really is calving ice very rapidly when it does that. And we've seen this in tidewater glaciers. And this is a picture of probably the best documented case of a tidewater glacier that's still in the process of dramatic retreat. And the shallow shoal is out here. It's been measured now that there's no grounded ice in the way. And it sat there for a long time, more than a century. But when it lost its hold on that shoal, it began to retreat. And this is about 15 kilometers, and it did that in about 20 years. And it was here in 2000. Right now, the terminus is right here, and it's on its way back, and this is where it gets out of the water. So we're quite sure this drastic retreat is going to continue for Columbia Glacier. The other Another important feature here I want to point out is this fjord, that's full of icebergs. They're not out here, they're here. Actually, that's good news for the oil industry, because the port of Valdez is right over here, and tankers carrying that oil go in and out. So there was great concern that when this glacier started to retreat, these big icebergs were going to just drift across and threaten the tankers. Well, alcohol was a greater threat to the tankers. But these icebergs are nicely confined by that shallow shoal. It tells you there's a shallow shoal there, and it tells you those icebergs are really big and they have really deep keels. That's the visible signature of a tidewater glacier in drastic retreat. This Google Earth, this Helheim Glacier, one of those big three glaciers in Greenland I keep showing, twin sister. This is exactly the same picture. You can go to Google Earth and just scroll around the perimeter of Greenland, and you will see this again and again and again. And now you know what it is. It's a glacier that's retreating so fast, you've got big icebergs, and there's a shoal there that's keeping those icebergs confined to that fjord. But that's a glacier that's retreating rapidly. And that's where Greenland is losing all this ice. Now remember, I told you that these tidewater glaciers will continue to retreat until that terminus gets into shallow water. Well, let's peek underneath the Greenland ice sheet. Let's not give it time to isostatically adjust. Let's just do this quickly. Let's lift up the rug, take a peek. All those blue areas are where the bed of the Greenland ice sheet is below sea level. And this is where Jakobshavn Glacier is. This is where Helheim Glacier is, and we think there actually is a direct connection here. And there is no stopping point. There's no physical reason if you apply the tidewater drastic retreat from Tidewater Glacier analog to Greenland and what we see happening, there's no reason that those outlet glaciers won't just eat out the heart of the Greenland ice sheet. We don't know how fast that ice is going to come out because we don't have the good quantitative numerical models of ice flow that we're still working hard to advance to the point where we can do quantitative predictions. But waving my arms, there's no reason that the Greenland ice sheet's fate is not sealed by the drastic retreat of those outlet glaciers. That's a sad story, but that's the story I'm telling, and I'm sticking to it. Antarctica, same thing. Those big explosions I put on the other, two of them were right here, one of them was right here, another one was right over here. Again, most of the West Antarctic bed beneath the ice sheet is well below sea level, not just 100 meters, but 1,000 meters below sea level. Those are deep marine basins. And again, those outlet glaciers, there's no reason they shouldn't be draining the entire marine-based part of the West Antarctic ice sheet and perhaps similar over to the East Antarctic ice sheet. We're talking tens of meters of sea level now, but we don't have a time scale for it. Won't happen tomorrow. I scare kids when I talk about this, so I tell them it won't happen tomorrow. Don't worry, it won't happen tomorrow. But so this really is the end of the story, and it is a disturbing story because we are concerned about how ice sheets are going to be contributing to an accelerating increase in sea level. That's what we see. So leaving you with the important messages, I conclude with this slide that ice sheets are waking up. They are giants, they hold a lot of ice, and they are becoming more and more active. And it's the water that's killing the ice sheets. The actual physical processes we think are fairly simple. Our future will contain less ice. It's always happened when the world has gotten warmer, and higher sea level. How much and how soon, we're not too sure. We're still working on those details. But the best number we give to policymakers and decision makers is expect 1 meter by 2100. That's a comfortable number for us. That doesn't push the physics hard at all. We are working, we're pushing hard as ourselves to get these process studies completed so we can give more credible quantitative predictions. And we're going to get there. I mean, we're working on using the models such as they are and imposing certain climate scenarios and letting the models do what they do well to help us refine these predictions. And that's probably going to go into the next IPCC report. That's sort of a drumbeat that we're marching to, but probably even better predictions for the report after that. But that's definitely, you know, we hear the message, we hear the questions, and we're trying to get the answers as quickly as we can. So treat this as sort of a status report. That's what's happening in the polar regions where the ice sheets live. And but it does affect you directly, and it will affect your kids, and it will affect their kids. Higher sea levels in our future, and this is why. So with that, I thank you for your attention, and I'm happy to answer any questions that you have.
So we have time for a number of questions.
How do you measure the height of the ocean, especially with an era of the order of a millimeter?
It's with altimeters that can measure range to, typically radar altimeters are good to about 1 centimeter, and position the satellite with GPS. And you know, you average data over arcs because you're over a fairly flat ocean. So averaging helps you beat down the errors, and you can get precisions of about 1 centimeter for areas of about 10 or 20 or 30 kilometers long. So the satellite altimeter is really sophisticated. And you know, you put in tide models and solid earth models, and you have crossovers, so you go over the same area in different directions at different times. There are ways to beat down those errors, but they're good to about it.
Matter because you work in one place.
Yeah, yeah.
Because it's not smooth anyway. Right?
Yeah, yeah. Yes?
Another factor you hadn't talked about, wonder about that's the methane that's covered, that's buried under the water, the seawater.
Yeah, yeah.
With the temperature rise, the temperature release,
Yeah.
coming off the whole model.
Yeah.
Talk about that.
I can talk about it. I can't give you very much good information about it. I don't think very many people know very much at all about that, but they know enough to be worried. And I can tell you that when we started to see the ice sheets change and we realized how much we didn't know and we were worried, the more we knew, the more we worried. So I wouldn't be surprised if the submarine methane release is somewhat similar story. Because the estimates I've heard of the potential amounts of methane that are there are just scary big. And I think most people know that methane is a much more effective greenhouse gas than carbon dioxide. I don't know how much the temperatures of the water will change. Certainly you need that to release the methane because it's frozen. And a lot of this is happening underneath floating sea ice. Whereas what I was talking about here in my expertise is more the grounded ice. So it concerns me, but it's not my particular field. But I'm sure that community is working at least as hard as we are to try to get credible numbers, because again, it could be a very big number in these scenarios that the IPCC puts together to estimate how the atmospheric composition will change over time. Yeah. There's a, well, let me go on this side.
If you have a 1 meter rise and warmer water, wouldn't that affect the severity of the storms that you might get? So the 1 meter might be 10 meters or more scattered when you hit the storms.
Yeah, I mean, we slip into the trap of just talking about one number and saying, sort of implying that that's uniform. It's anything but uniform. In fact, it matters a lot where that ice comes from in terms of how that additional water is distributed globally. And yeah, and there are some people who are above that mean number in terms of the sea level that they experience at their shoreline, and there will be other communities that are below that. So there's some winners and losers in that regard, and the tectonic effect may be something that again puts you on the good side or the bad side. Like Louisiana is a triple whammy loser, because sea level's going up, Louisiana is going down because the Laurentide ice sheet used to push Canada down and Louisiana up, and now the Laurentide ice sheet's gone, so Canada's rising like I don't know, what, centimeter a year or so, and Louisiana's going down just from that seesaw effect. Even if sea level was constant, globally, it would be rising in Louisiana. And Louisiana is made up of Mississippi mud sediment that itself is consolidating and compacting. So it loses on every side of that issue. But you're quite right, sea level rise is not uniformly distributed. And so that does play into it. And there are more detailed calculations of, okay, if we're going to dump more ice from Greenland, how will that be distributed globally? Actually, Greenland will then start to rise, so local sea level around Greenland wouldn't change as much as it would sort of in areas that are some hundreds of kilometers away that would experience this seesaw effect. So it's because Greenland pops up and then those other places go down. So there are people that work on that and quite carefully have detailed deformation models of the Earth that account for these temporal changes and the non-uniform characteristic. I can say if a lot of water comes from Antarctica, the west coast and the east coast of the U.S. are on the bad side of the mean. It will be a little bit worse than average, whereas Europe is actually on the better side. But those are fractions of the overall meter. Yeah.
Question on the basin beneath the Greenland ice sheet. That's fresh water, is it not?
That's ice right now. I mean, it's displaced by the ice sheet itself.
Oh, all right.
Yeah.
The question is, as in a tidewater glacier, does the ocean, the seawater, invade that basin as it retreats?
Well, as the ice retreats, yes, but it doesn't sort of sneak underneath the ice sheet. The ice actually has to evacuate that area.
Or through the moraine.
It just comes over, yeah.
But anyway, the point is that that's much warmer water.
That's right.
And so it accelerates the
That's right.
on the base.
Yeah, I didn't sort of talk about the temperature effects, but you're absolutely right. Warmer water gets to the ice and it just makes the bad story worse. Yeah. Yes?
It takes time to do the studies to improve the predictions and reduce the uncertainty. Can you win against the time needed to make the predictions? Make a prediction 10 years from now, but it takes 10 years to get the data to make a decent prediction.
We've got a decent prediction now for the next 100 years. So no, I think we can stay ahead of the curve. The uncertainty bars are still pretty large. But for decision makers, I think their focus in the past has been on the uncertainty, saying if the uncertainty bars are large, I shouldn't do anything. That thinking is starting to change, that they're beginning to appreciate that the uncertainty bars are not what to focus on, but the mean. And we really are, but we scientists have to do a better job at communicating that. So they don't focus on the uncertainty, but they focus on, this is the best number. Yes, we have some uncertainty, but you have to plan to the best number we have, not just stick your head in the ground and hope that it's going to be on the good side of an uncertainty range. And I'd have to say that the people on the other side of this debate have always been emphasizing the uncertainty, and scientists are just suckers for that because they love to start talking about the uncertainty. But we have to keep in mind who it is we're talking to and the fact that we're trying to influence their decisions so that they're making smarter bets. But it is a bet. There still is uncertainty, but we want them to make smarter bets, and so we try to get the numbers as good as we can, but focus on the number, not the uncertainty. And we just have not been delivering that message, and not effectively enough. We just have to get better at it. But yeah, we can stay ahead of the curves. Yeah. Yes?
Any positive example of a nation where policies are being put in place to respond to that mean?
England? The Netherlands? Yeah. They know. They've been below sea level for a while, and the Thames has been worried about the Thames barrier that closes during periods of high tide, so that there isn't damage to waterfront facilities along the banks of the Thames. They're closing that Thames barrier more and more frequently, and they realize they're already designing the next Thames barrier for conditions sort of 50 years out. So there are investments being made by a number of countries, and that are taking into account the reality of increased sea level. The Maldives was represented at Copenhagen, and they were saying they were looking for places to move. So can we start migrating our people to your country? You know, they get it big time. And there are communities along the eastern seaboard. I've been part of groups that have talked to planning boards in Norfolk and Wilmington, where they can finally connect the dots. They can see sea level going up a meter, and they had just come from a meeting where they were discussing the construction of a connector highway between two big expressways. And at one point, it dipped down to 2.5 feet above sea level. And they said, we want that expressway to be there 50 years. It's probably not a good idea to build it along that route. We probably better route it a different way. So we're finally starting to get some traction, even at the local level in this country. So I'm actually fairly encouraged that people are starting to get the message in little pockets, and it will get better and better over time, I think, because people will finally realize that this is our future. It's not a liberal conspiracy. Yeah.
I'm sure you have a good answer to this question.
I hope so.
It has to be asked. The sea level goes up and down in Maine much more than 1 meter twice a day. So that makes me a little less worried than I was. And then when I thought building a seawall 1 meter high doesn't seem very difficult. And there must be something wrong with this line of thinking.
Well, I mean, again, we're talking mean numbers, the 1 meter. And it's, well, my 1 meter. And everything bad but all the natural variability, I mean, tides, storm surges, hurricanes, you know, the full spectrum of harm that comes from the oceans is on top of that. So sea level, mean sea level is just the launching pad. So the launching pad is going up. So everything bad that happens will get that much worse by the increase in the mean. But, I mean, I'll tell the story that when we were in Norfolk, we had the travel agency that arranges travel for NASA people is based in Norfolk. And in Norfolk, we were told that when they normalize all the storms, the hurricanes and the nor'easters that they've had in Norfolk, based on sea level at that time, normalize that, it's already showing that the nor'easters are at least as damaging as the hurricanes, in the sense that they have more frequent nor'easters than they have hurricanes. And the accumulated effect of 5 nor'easters is the equivalent of a Category 2 hurricane. So, as fate would have it, 2 weeks after that, I was on travel and I had to contact my travel office, and they were shut down because Norfolk was having a nor'easter. And the travel office was flooded, and they weren't working that day. So everything bad. So the message there is that everything bad that the ocean does will get worse as sea level goes up. So 1 meter rise in sea level does matter, even if you have 2, 3, 4 meter tidal variation. Yeah, it still matters.
We should thank our speaker again.
Thank you.